This is Unsiloed, brought to you by Alumni FM, connecting people through stories.
Welcome to Unsiloed. This is Greg LeBlanc, and I'm here with Pedro Domingos, who is a professor of computer science at the University of Washington, and also the author of this book right here, The Master Algorithm: How the Quest for the Ultimate Learning Machine Will Remake Our World. Welcome, Pedro.
Hey, thanks for having me.
So, when we think about machine learning in today's world, it's kind of like the new philosophy, right? It covers so many different aspects of cognition, of learning, of knowledge. I think even in places like Berkeley, we are including, we call it data science, but we're including data science as almost a required class for every undergrad. And I think this is sort of meant to be their exposure to what we might think of as critical thinking and reasoning and logic, which they might have gotten from some other class. Back in the Middle Ages, they might have had to take a class in, logic and read Aristotle and so forth. Have computer scientists become the new philosophers of our age? Have they kind of supplanted psychologists and education theorists and philosophers and everybody else?
I don't think computer scientists have supplanted psychologists and philosophers and so on. I do think, however, that computer science and machine learning in particular changes the way we do everything in a very profound way. If you look at science, more than anything else, its progress is determined by the tools that are available, right? Galileo was Galileo because he had a telescope. No telescope, no Galileo. And the examples go on. And the thing is that computers are really the most extraordinary tool for science, among other things, but for science in particular, that we have ever created. They just magnify our ability to do things in a way that was, I think, hard to imagine even 50 years ago. So in particular, if you look at a lot of science classically, they were like the hard sciences. That were the sciences where you could do math, right? But math, with our poor brains, and pencil and paper, people have been amazing, the Newtons of this world, in how much they can pull out of that. But really, it's very limited. Computers are machines that do math by nature, right? A computer does more math in a microsecond than I do in all my life, right? And so now the question is, how do you harness that, right? Well, you can build models. Science is about building models of the world one way or another. You can build models that are vastly more complex and vastly richer than before. Coupled, of course, with enough data that is commensurate with the complexity of the phenomena. And again, if you look at physics, right, it took off because, anybody could watch something fall from the Tower of Pisa, right? Where social science is a whole different ballgame. Mm-hmm. But with computers and with data, and with, the algorithms that's actually the role of the machine learning researchers to come up with these algorithms, we can actually, in some sense, we can turn the soft sciences into hard sciences, which is I'm glossing over a lot of things here, but, a lot of the questions that used to be philosophical, think of, Wittgenstein and, his two phases, right? The two phases of Wittgenstein are actually two schools of AI. Except, and he was very insightful in both of them, right? Despite their contradictions. But the thing is, as much as that was great, we are so far beyond that now. Because we no longer sit on an armchair thinking, oh, how does thinking work? We build the thinking machines and we see how they work and don't work, and we learn from that. So yes, this is, I think, a revolution. And I think the revolution is just beginning, right? I've seen over the course of my career, machine learning spread, from one field to another. And, economics actually, I think, is a nice example, right? In the last decade, machine learning has taken off in economics. Maybe it should have taken off earlier. Mm-hmm. But another pattern that I would say, and actually this goes back even to physics, and this is partly speculation on my part, but I think it's going to be very important in the future, is that so far we've seen machine learning be used largely as a tool to help in making sense of a lot of experimental data. And then the human scientists, the human theorists still do the heavy lifting, right? So, CERN or the Large Hadron Collider is a great example, right? Like that thing couldn't work without machine learning almost because the sheer volume of data that it puts out is right. But the machine learning is not doing the job of Newton yet. But I think the time is coming very soon where the machine learning is going to be doing the job of the Newton, right? If you think of like, the machine, like a lot of science, you can divide into three phases. There's data gathering, right? Most of science is data gathering. Right?
This is like the Tycho Brahe stage that you reference in the book, right?
Yeah, exactly. And, by God, like that part, we've got data gathering up to us, right? We no longer point like a telescope at the stars once. We do these massive sky surveys of billions of objects, like every, little, fraction of an arc of an angle, right? It's on a completely order of magnitude. And now machine learning today, right, to continue with that analogy that of course I have in the book, right, is doing what Kepler did, is to come up with phenomenological laws by basically fitting curves to the observations. And, this is already very powerful, right? But the real science is the Newton stage where you actually have these universal laws that are not just, like these universal laws actually, typically, if you look at, for example, what people do in physics today, a lot of them doesn't come directly from the data. They are trying to fit the phenomenological laws, but they are far, far more general. And I think, when all is said and done, we are going to have a lot of these laws that were produced by machines because at the end of the day, they're going to be able to do it much better than we do, right? And this, I think, is going to change dramatically, science across its entire spectrum. One maybe very important example and good example is biology, right? Biology, in some sense, is a physical science, right? It's just phenomenally complex and full of random stuff, right? There's no human biologist that can understand all of the biology of the cell, right? But a computer can, and it will, right? And then it'll be an interesting question how we and those computers communicate, but I think, this is coming.
Well, so you talk about the creation, we jump in the gun a bit, but you talk about the creation of this master algorithm, and you talk about it through the lens of these different tribes of machine learning. But aren't you really talking about a unified theory of learning full stop, right? I mean, we have a unified kind of domain of physics, which integrates all of these different rules that we've learned about the world. We've got sort of a unified theory of biology, which kind of unifies these different things that we've observed separately. And when you talk about this unified field theory of machine learning, isn't this really a unified field theory of learning full stop? Because each of these approaches to machine learning, aren't they also approaches to learning in general?
Of course. And in fact, part of what makes machine learning interesting and the book fun to read, I hope, is that the different paradigms of machine learning all come from different sciences, right? Evolution. So, we're looking for a learning algorithm. Where could we take inspiration? Well, evolution is one, right? Evolution made us, right? That's pretty darn good, right? Or, there's like neuroscience. The brain is the greatest learning machine. So let's be inspired by that, right? Or the scientific method, right? Let's automate the scientific method. That each of these is a school of machine learning. But as you say, you can call it evolution, you can call it learning, you can call it discovery. These are really all facets of the same thing, right? And in machine learning, we're at the stage where, these paradigms, they have decades of research behind them, but there's a deeper commonality between them, right? And I think finding them is the quest for the master algorithm. And it is a great unified theory of machine learning, right? And a mature field has such a theory. Many fields have not matured to that point. You could argue that some of them won't. But I really think that at some deeper level, evolution and the brain's learning and so on are all different aspects of the same thing. And this is what we have been groping towards, if you will.
So I want to step back a little bit and talk about the different kinds of stages historically of how knowledge is created and transmitted. And I think you make the argument that there have been a couple phases. We're in the fourth phase, which is probably the most dramatic phase. And you talk about evolution. And so evolution is really, knowledge is embedded in the DNA. And so organisms are kind of hardwired do certain things, and that's based on knowledge that is, hardwired or codified. Then you talk about, how an individual organism can kind of start adding data, learning data, observing in the environment. And then there's sort of an if-then baked into the organism that tells it what to do in response to that new data. And then you talk about culture and how kind of you can learn not from your own behavior, but from the behavior of others. And then you say that computers represent the fourth step in the development of kind of knowledge capture and transmission. Is that, I mean, that seems like a radical claim. Is this really sort of part of a continuum? Is this sort of a discontinuity? Should we be, when people think about the first three as being natural phenomenon, and then this sort of seems like a non-natural phenomenon. Is this part of our extended phenotype, right? To use the Dawkins terminology?
It is indeed very much part of our extended phenotype, but I think the more important point here is that technology is a natural phenomenon. It's a very human-centric thing to say, oh, there's nature, and then there's what we make, and that's technology. That ain't so. We're natural. Everything that we make is natural. It's technology, and technology is part of nature, right? And this, I think, will become increasingly apparent as time goes by, right? A steam engine doesn't look very natural. But a computer, right, when you start to look at some of the things that computers make, they look very comparable in flexibility and richness to what nature can do, right? And machine learning is precisely a step where, like, instead of, us having to program the computer step by step to do something, they kind of come up with it by themselves. Again, looks a lot more like nature. And of course, the other one is, like, if you look at biotech is going, right? Biotech erases the difference between technology and nature. There is no place in biotech where nature ends and technology begins. And 50 years from now, biotech will be, much more widespread than it is today. And so this notion that, computers are technology and that things are nature, this is going to dissolve. Having said that, these are discontinuities. The emergence of life was a discontinuity. The emergence of nervous systems and neural learning was a big discontinuity. And the emergence of culture is another big discontinuity. And computers are another one. And now you say this is a radical claim. Maybe it is, but actually, if you look at it, it's a claim that is hard to dispute, that all of these are ways of acquiring knowledge, right? With machine learning, a computer can acquire knowledge from data. It still needs hand-holding to set things up. But then once you turn it on, it starts discovering knowledge from data, right? Like a lot of knowledge that we have in biology and other areas was discovered by computers, right? So it is a way of discovering knowledge, like the other ones obviously are. And then very importantly, it's a way of discovering knowledge that is orders of magnitude faster than the others. That's the thing, is that evolution, it did make us, but it's excruciatingly slow. And then, like neural learning is dramatically faster. You're actually learning within the lifetime of a single organism. And then culture is even faster because, before culture, a mouse or a cat, well, they learn a few things during their life, but I can read a book, right? And learn an entire field in an afternoon, right? And then computers are even faster than that, right? And here's something that we all know, but don't quite realize the import of. The speed of acquiring knowledge by culture is limited by how fast we can talk or read, right? But we talk at, 100 bits per second, not even, right? I mean, if I was talking at 100 bits per second, that would be too fast.
Someone might be listening to this at 2x right now. So.
There you go. Yeah, that's when you get closer to 100 bits per second. So let's call it 100 bits per second. Well, computers can talk to each other at 100 gigabits per second. A billion, like two computers say more to each other in 1 second than all of humanity talking during that second. So the speed at which that knowledge can be transmitted is just mind-bogglingly different from what we're used to. And, we are only beginning to come to terms with what this is going to mean for us.
So you reference space complexity and time complexity as kind of constraints on learning. Are each of those transitions kind of expanding the frontier and kind of overcoming those constraints? Is that one way to look at it?
Well, yes. So the amazing thing about computers, right, by the church Turing thesis, is that they can do anything, right? This is actually what attracted me to computer science, is that, and again, I say that in the book, it's like you're a little god when you're a programmer. You can create worlds, right? But the serpent in the garden is that you are limited by the available amount of memory and the processing speed, right? So you can only create within this box. And really what a lot of computer science is just making the box bigger.
Mm-hmm.
And we make it bigger by Moore's law in leaps and bounds, right? If you zoom out, right, it's like the speed at which we're making the box big is amazing. Having said that, no matter how big we make the box, it will always be too small. This is why, like many other goods, there is an unlimited appetite for information processing capacity. If you gave me a computer the size of the universe, I would exhaust that. Working at the speed of light, every subatomic particle is a memory state. I would exhaust that just to play chess. Right? Just the game of chess has more states than there are atoms in the universe, let alone real problems. Right? So there's no limit to how much of that computing power we can use. And in fact, you could look at this whole process that started with evolution, and we get exponentially better, at terms of and each of these ways of technology usually starts out very crude, including nervous systems and culture and computers, right? And then it becomes very good, and then another one comes along. But in a way, what all of this does is it lets evolution, in the broadest sense, including technological evolution, explore a larger landscape in a finite amount of time. Right? Evolution is a race, right? If I can try out more ways to play chess than you can in a given amount of time, I win. That's actually how AlphaGo beat Lee Sedol, is that, AlphaGo played more games in those 3 months where they were training it than Lee Sedol did in his entire life by orders of magnitude. It played millions and millions of games, and that's why it worked.
So I remember when you came and spoke in my class a couple of years ago, you were talking about how when you first entered the field, it was in the midst of an AI winter, right? One of the many, I guess there have been, and I think that it's probably safe to say that there will never be another winter again. Was this winter? I think the winter you described is really right around the time when the kind of knowledge engineering approach had kind of run its course, and really, learning hadn't yet kind of kicked in. So what was responsible for that kind of leap into understanding the importance of learning? Academically, philosophically, how did this kind of transition happen in the academy and in the field of computer science?
Well, it really has to do with this difference between learning the knowledge or having people input the knowledge. And ironically, in the early days of AI, learning the knowledge was very much what people believed in. In fact, Alan Turing said so. Like, this is the way AI is going to happen, is by computers learning. Why wouldn't we go that route? That's what humans do. Right?
So it's just that we didn't have the technical ability to learn, or we hadn't really thought through the methods. I mean, so we knew philosophically that this is where we had to go. We just kind of couldn't figure out how to make it work.
It was actually several things. And I think there's lessons in knowing what those things are. One of them was that the early learning algorithms were actually not very powerful. People got very excited about algorithms there were these stories in the New York Times in the 50s and 60s about the perceptron algorithm is going to lead to, the first brain and, et cetera, et cetera. And now we look at that and what were they thinking, right? All this algorithm does is create hyperplanes in hyperspace, right? Like, how is that intelligence, right? And so those algorithms were not nearly as powerful as they need to be. We actually now have much more powerful algorithms in many ways, right? But of course, I think 50 years from now, the algorithms that we have now will look as silly as backprop, as actually backprop, which is what we have now, that makes the old perceptrons look silly, that will look silly. So this is one aspect. Another obvious aspect is that what powers learning is data. The reason learning has taken off is that, it's like a rocket that's fueled by data, right? And data is like, fuel is now super plentiful, right? If you can make learning algorithms that scale, then, having more data just means more knowledge for free. At some point, no human knowledge engineer can compete with this, right? And of course, more computing power to handle that is a necessary condition, but that is also, here now, right? Which it wasn't back in 1950 or even in 1980, right? In the 80s, which is when all this happened, we really didn't have the computing power. There was already learning, but it was not very powerful because, we only had so much data and so much computing power to learn. But another one, which is actually, I think, in some ways, the most important one, is that there really was a philosophical change in our view of what it takes to build intelligence. Right? The old knowledge-based AI, the idea was, I'm going to teach a computer to be a doctor by interviewing doctors and writing down rules about how doctors do diagnose. And the thing is, that does not work. It creates a system that is very narrow and very brittle. For many reasons, one of which is that it's actually very hard to extract knowledge from people. And I'm not even talking about as like driving a car, right? I know how to drive a car. You know how to drive a car. Nobody in the world knows how to program a computer to drive a car. It's just too complex. It seems easy for us, but that's because evolution spent 500 million years creating us to do stuff that's similar to driving a car, and it's not exactly driving a car. What we can do, however, is we can just, take the diagnosis that doctors produced and say like, oh, this X-ray had a tumor here, and this one had no tumor. Or like this person, they were driving a car, they made a left turn when you saw this on the video. This is dramatically easier for us, the AI researchers, to then at the end of the day have someone who knows how to do radiology or something that knows how to do radiology or how to drive a car than before. And, if you asked your average AI researcher in 1985, they would have disagreed with what I just said. They said like, we don't know how to learn. We don't have enough data. The problem is too hard. You just have to tell computers what to do. And now, this has come around 180 degrees. Maybe even too far, because in some ways there's still some knowledge that humans can contribute, but but clearly using data is the way to go.
Did this echo some ideas in other disciplines as well? I mean, I'm thinking in linguistics, right? So I think we probably now have deeper faith in kind of more of a learning model with respect to things like language and so forth. We know a lot more about brain plasticity than we did before. Maybe in the world of neuroscience, even people thought that, the brain had these dedicated modules and wasn't nearly as plastic as we now believe it to be. Have those other disciplines kind of learned that from computer science, or, has computer science learned it from those other disciplines? Has there been a lot of back and forth communication between the computer scientists and their view of learning, and then the people who study humans and how they learn?
Well, there is a lot of back and forth that in both directions, because again, a lot of the major ideas in AI came from these other areas, and psychology, linguistics, neuroscience are major examples. But then also in the other direction, right? So a lot of ideas in psychology, linguistics, and so on have been influenced by computer science. And this same, opposing schools of thought that exist in AI, that exist in psychology and exist in linguistics. This whole notion of should you learn versus is it innate, right? Well, that's the nature versus nurture dilemma, right? Going back, hundreds of years at least. And again, if you look at the same
all the way back to your all the way back to the ancient Greeks.
Well, yeah, indeed. Like, Aristotle and Plato, you could see this as being what their difference is about. And, it's all been playing out, but now it's played out with computers at a greater speed. But the debates in many ways are still the same. Mm-hmm. And if you look at, for example, Chomsky, right? He totally panned the idea of learning language from data, right? In a way that seems absurd to us now. But again, to be fair to him, you have to realize that what he was panning was the algorithms that were available then that were, incapable of learning language very well. But even those, a lot of the early speech recognizers even up to 10 years ago, they were based on what Chomsky thought was a joke. Turns out it wasn't a joke, right? There's a lot of things about learning that are kind of like counterintuitive, but and there was this whole school of linguistics which is still dominant, right? In the field of computational linguistics, machine learning now dominates. But in the field of human linguistics, if you will, right, the Chomskyan ideas, even if their critical validity is in shreds, are still what most linguists believe in. So these debates are very much there. And even in neuroscience, to take another example, there's a lot of people who say, and again, neuroscience is very unsettled because we're very far from understanding almost anything about what the brain is really doing, other than at the very, the level of the individual neuron. There are a lot of people who say like, oh, a lot of this learning is an illusion. It's just things that are wired into your genes that manifest themselves at different stages. And, they take in some stuff from the environment, but for the most part, your brain seems to be learning, but it's really just developing, right? And where exactly the truth lies in all of this, the answer is we don't know yet.
Mm-hmm. Now, you walk through the five, you're kind of like an anthropologist when you go through and talk about these 5 tribes of machine learning. Before I read this, I had no idea that there were these 5 completely different groups of theorists, all of whom seem to believe that their approach is the one that's capable of knowing everything. And so what I found interesting about this from an anthropological perspective is that, in a lot of disciplines, like in economics, we have empiricists, we have theorists, we have experimentalists. None of them claim that their method is the best method or the only method. In law, we have, we use deductive reasoning and inductive reasoning, and we keep flipping back and forth. And I think, everybody understands that, each approach is going to illuminate certain things, and you got to be able to kind of flip back and forth between these different approaches. Is it true that the people within these tribes all believe that they hold the key to understanding, all knowledge? Or do they, fully understand that they're really pursuing only a, one kind of approach, which will encounter limits at some point?
There's a spectrum. Again, I think looking at this as anthropology of science is actually the right idea. And people do anthropology of science, right? And having different paradigms competing in a field is actually common, right?
But even when you use the word paradigm, I mean, when we think of paradigms as, one approach supplants another approach, which is then supplanted, and then those old approaches are kind of flushed down the toilet. I mean, no one, the Ptolemaic school and the Galilean school are not still kind of, competing with each other.
That happens, and you could say that that's progress. But it also happens that there are competing approaches that carry on competing for a long time. Take statistics, right? Relevant to machine learning, right? Frequentist versus Bayesian, right? This thing has been going on for hundreds of years, and it shows no signs of going away. And the Bayesians, again, the Bayesians in statistics and the Bayesians in machine learning, deep down, they truly believe that theirs is the only correct answer.
They're very dogmatic, right?
Yeah. Again, I make this analogy in the book of Catholics versus Protestants, right? The frequentists are more like Protestants. Anyone can set up their own church and preach, and Catholics, the Pope, the truth comes down and so on. And honestly, I actually think the frequentists and the Bayesians both have their merits. And at the end of the day, there's less of a difference between them than you might think at first sight, right? So again, and you can say this about AI more broadly, you had a lot of very pointed arguments between people in AI. But at the end of the day, the problem is that nobody for sure knows what's going on. So we are not yet at the point where one paradigm could prevail over the others. And my point of view is that, and this also happens in science, is that often these points of view, one thing that happens, and it has happened within certain subfields of AI, that one paradigm just, basically brushes the others away. Right? It happened, for example, with graphical models. There are all these different ways of dealing with uncertainty and whole conferences about them, like fuzzy logic this and evidence calculus that. But then, graphical models, meaning Bayesian networks, Markov networks, they swept that away, right? If you look at those conferences now, there's no fuzzy logic or those things like that anymore, right? So that does happen in AI, and often for good reasons. Sometimes actually for bad reasons, but often for good reasons. But it also happens that different paradigms get unified. So think of light. Is light particles or is light waves, right? Particles, because of Newton, people, believed they were particles, right? And then there was like this incontrovertible evidence of, wave-like behavior. And, circa 1900, light was waves. There's just, case closed, right? But then there were behaviors that just couldn't be explained by that. And what we have today is a very deep unification of the two, where we know that depending on which angle you look at light from, you see it behaving as particles or waves, right? So it can also happen that what you get is the unification of these paradigms. And I believe that in machine learning, we need the unification for the following reason, is that each of these tribes has their master algorithm. There are certain problems that master algorithm solves very well, but there are others that it doesn't. And to get AI, we need to solve all of them. And these algorithms, they can't do magic. So I don't see, again, the hardcore people in each of these tribes really do believe that theirs is the answer. And again, decade by decade, this is a fun history of machine learning, is that decade by decade, one another paradigm is on the rise, right? And right now it's, of course, neural networks, better known as deep learning, but this is their third comeback, right? They come, they rule for 10 years, and then they go away for 20, and then they come back in another 10, right? And for all we know, the same thing is going to happen again. But usually the people who are in the dominant paradigm are the ones who have a tendency to believe that, like, hey, we're going to do everything with this. And the others are like, oh no, but you have to combine it with ideas from us, right? And then what happens usually when you fast forward 20 years is that some other paradigm is dominating, but the lessons of, what the others did before have been learned, right? It's not like we've gone back to the beginning. There's a circular element to the trajectory, but there's also an element of progress. It's more like a corkscrew, right? Ideally, we'd go straight to the end without all the turns, but, we're still making progress is, I think, what's important.
Yeah, I think from the outside, everyone would think that kind of deep learning neural networks, right? The connectionists, Jeff Hinton and his crew, they're sort of, that's sort of, they've won. It's over, right? That's where all the investment is. I interviewed Cade Metz recently, who wrote a whole book on the rise of the connectionists and neural networks and back propagation. And, I think a lot of people equate the two things. They think, well, that's what machine learning is.
No, actually, these days, and again, this is interesting to observe, a lot of people equate AI with deep learning, not even just machine learning, AI. And one of this is going to be computer science that's equated with deep learning, right? Because again, there's a big difference between the stories that people see in the media and what's going on, right? There's a lot of machine learning researchers don't do deep learning. There's even more machine learning practitioners. For most applications, the best methods are still, and this is documented, right? This is the empirical evidence. The best methods for most applications are not deep learning, right? And then there's all these areas of AI outside of machine learning, right? If you go to an AI conference, not when a machine learning conference, like ICML News, but an AI conference, there's knowledge representation, automated reasoning, distributed AI, multi-agent system, et cetera, right? So AI is a vast field, but people get a very skewed representation of it in the media, because the media, of course, is focused on where the most exciting progress is happening, and certainly overwhelmingly in the last 10 years, that's been in deep learning. But for people who know the field, right, all of this brings a smile to our faces because we've been here before. We remember when, the symbolic paradigm was everything and neural nets were dead. Neural networks were boring. There are a few, diehards like Jeff Hinton and Yoshua Bengio and Yan LeCun who didn't give up. But, I know those diehards in other fields right now, and maybe, 20 years from now, they'll be the ones going like, what the hell was all that, right? We got the answer. So we don't, on the other hand, sometimes, as we just saw an example, right? Like, it is a case that one paradigm for good reason prevails over the others, right? So we don't know how this will turn out. But I think anybody who wants to understand what is going on in AI should be very suspicious of the notion that, like, oh yeah, it's all deep learning. Deep learning, at least as we have it now, there are some very fundamental answers that it does not have. Maybe they will arise within deep learning. Maybe they won't. And the truth is, we don't know yet.
So is the kind of success of each approach a function of the problems that we're trying to solve at any particular moment? One of the things that kind of really surprised me when I started learning data science is the extent to which so much of it is trial and error, right? When you're teaching data science for, at the level of the business school or whatever, it's just, you learn naive Bayes, and then you learn nearest network, and you learn decision trees, and you just kind of try them all out and see which one works. And I think an experienced data scientist would probably say, well, I can predict ahead of time with this type of data set, this thing might work best. But from the practitioner perspective, nobody cares about the theory. It's just, I've got a screwdriver, I've got a hammer, and I've got a Phillips head, and I'm going to try them all until I get the screw out. Should we be thinking about machine learning as just, hey, there's just a bunch of different tools out there, and right now it seems like everybody wants to unscrew Phillips heads, and maybe in a few years everybody's going to want to unscrew regular screws, and a different approach is going to rise to the top.
So you're right that machine learning is an enormous amount of trial and error, but that shouldn't surprise anybody, because evolution is trial and error, and so is scientific research. Really, science is an enormous amount of trial and error, and every now and then there's something that really hits the nail, and that's what people hear about, but they forget everybody's spending, years in the lab doing all the trials that turned out to be errors. So this is what you'd expect. But now, the whole thing about trial and error is that, Shakespeare also wrote by trial and error. And monkeys can try to write Shakespeare by trial and error, but they'll never get there. So the speed at which you do trial and error is really the key, right? And the thing is that the reason good machine learning people get paid enormous amounts of money, right, in industry, is that a better machine learning person with the same data computing power can make progress, tens of times faster than someone, there was this famous saying, I think it came from Bill Gates, that, a really good software engineer is worth 100 average ones, which is true. And it's very different from, a good factory worker is maybe worth 10, right? But with software engineering, it's because then once, you have to write the software, but once the software is running, right, the same piece of software will run an infinite number of times. With machine learning, there's an even bigger multiplier. So a really good machine learning person is worth, 10,000 average ones, or you just get some infinity, because they'll get somewhere that gets in. And a lot of it is, there's a lot to know. There's a lot of these techniques, but a lot of it is the black art, is the part that you can't, in the same way that you know how to drive a car but can't explain it how, you know how to do machine learning because you have a more refined sense of what is good for what and what to try. And for any given problem, at the end of the day, the best algorithm is almost never an existing one. Because it's, what a machine learning algorithm does is not magic. It's incorporating knowledge, and knowledge will be different in different domains. Now, there are broad classes of domains where the same knowledge is relevant, and indeed, different paradigms tend to do well at different problems. So deep learning does very well at perceptual problems, because again, these things were inspired by the neurology of the visual system, and et cetera, et cetera. So not surprising, they do things like object recognition. But if you want things like common sense, high-level reasoning, et cetera, well, then, symbolic approaches are good at that, and so on, right? So there are different classes of tasks for which different methods are better. But then there's a higher level of refinement that really involves, having a PhD in machine learning, unfortunately. Right? What we want is to make things to the point where the practitioner, instead of having to try 1,000 different things and needing a PhD in machine learning, can just understand their domain and talk with the machine at the level of models, right? Not at the level of particular techniques, and actually, have a better time and make more progress that way. And really, this is what a lot of the goal of us machine learning researchers is. And, we've come a long way, right? But there's a lot more still to go.
Well, we've seen a lot of automation happening at the level of, basic data science. And, I mentioned that a good data scientist is somebody who does a lot of trial and error, but can't we just kind of apply machine learning to that process? So, if we kind of know what the problem is that we're trying to solve, and we know what a good solution looks like, then why can't we just automate that trial and error process and just have, an algorithm that where we learn how to learn, right? Wouldn't that be a way of kind of integrating rather than coming up with a unified theory? Just sort of have a kind of a algorithm that selects which approach to use in which circumstances.
Oh, we can, and we do, because hey, machine learning researchers are very expensive, so the prime candidates for automation, right? Mm-hmm. If they're doing all this, just tweaking parameters and trying different, versions of things, then hey, I can have an algorithm that does that. And in fact, this is an idea that is almost as old as machine learning, and it's called metalearning. Mm-hmm. Sometimes it's called AutoML. And if you look at, for example, the big tech companies who very much have this problem, right? Like, what I hear, talking to people at these companies, large, medium, and small, is we are limited. Like the list of things that they want to do with machine learning just grows every day. What limits them is how much the data scientists that they have can do. So if I can automate it and do 100 times more, then why wouldn't I, right? But the interesting thing about this idea of, meta learning is that, like a lot of other things in AI, it has come and gone. Every 20 years it becomes popular. It's popular for a while and then dies out again. Right now it's very popular, right? And we'll see what happens. But you can see why it would be popular, but why is it not the answer at the end of the day, right? It's actually for a very simple and fundamental reason in machine learning, is that if you just try, the computer can try an amazing number of things, right? That's its power. But then it overfits. Meta learning is more prone to overfitting than the sum of the algorithms that it's combining, right? So, like meta learning was very popular circa 1990 something, but the problem is that the meta learners just overfit. And why wouldn't they, right? I tried not only every version of a decision tree and every version of a neural network, but all versions of both of them and combinations. People have like decision trees with perceptrons at the leaves, nearest neighbor with, well, you can imagine, right? But then you just overfit like crazy, right? Now we have more data, so we can push this out a little bit further, but eventually we will overfit, right? Or like the problem is that like the space is very large, and even with a data center at your disposal, you can't necessarily find the answer by brute force, right? If you could find the answer by brute force, you wouldn't need AI. Really, AI is the subfield of computer science that deals with problems that you cannot solve by brute force, even as simple as chess, right? So we need something else. And in fact, in the book, when I get to the chapter where we unify all the ideas, this is actually the first thing that I talk about, because it's the obvious one, is combining different models, right? Mm-hmm. And this is part of why it doesn't work. But there's another one, which is, it's very easy to combine things in a shallow way. Oh, you have paradigms A, B, C, D, and E. I'm just going to create a program that calls them as subroutines, right? Mm-hmm, and has some logic for deciding which one to do, right? This is, if you look at the bigger unifications in science, right? It's not like electromagnetism is a routine that calls electricity or magnetism or light, depending on what you're looking at. Absolutely not. They are really all the same thing, right? And you don't understand the problem until you know that they're the same thing. So this is what we're really looking for in the master algorithms, is not just some routine combination of them, but really deep down, why what they're really doing is all facets of the same thing. And I do believe they are all facets of the same thing.
Yeah. So, the philosopher in me wants to question as to why, the symbolic approach doesn't dominate all the other approaches. And the lawyer in me is wondering, why doesn't the analogical approach kind of, dominate everything? But in this podcast, I've been talking to a lot of biologists, and, they really, really think that the evolutionary model is capable of so much. And I remember I guess it was like 2000, 2001, I was teaching alongside a biologist, and everyone in the biology field had so much faith that these evolutionary models had universal applicability. And so why hasn't, I could have picked any of them, but what's been the thing that's holding back the evolutionary model? I mean, you mentioned how boosting and bagging, and there are all these other approaches out there. Why haven't they fulfilled the promise that they've shown? I was talking to Stuart Russell recently, and he said he just kind of dismissed the evolutionary model as saying it hasn't done anything for us, right? So what's been the major obstacle there? Because that seems like such a powerful way to select good predictors.
Exactly, right? So as a philosopher and, lawyer and, biologist, like you can see what the pull of all these ideas is, right? Let's take evolution, right? Again, this goes back to the 50s, and John Holland was the big person here. For a while, the joke used to be that evolutionary computation, or genetic algorithms, as they're also called, was John and his students and their students, right? And why did so? And again, what happened with evolution happened with the others. So we roughly know how evolution works, right? There's crossover, there's mutation, there's a population. You try them out, they score differently on fitness. The fitter ones reproduce. Great. Let's implement this on a computer. We do evolution on a computer, and we come back the following morning, and humans have evolved, right? This is the intuition, right?
Yeah.
Caricatured, but like it's a valid intuition, right?
Okay, and you get local optimums, and there's some problems, but at the end of the day, I mean, it does amazing things.
Evolution in the natural world does amazing things, right? Indeed, evolution in machine learning, computer science has not done too many amazing things. In fact, people.
Is this because we don't have the equivalent of, in other words, the subroutines don't work in the same way as, say, a piece of genetic code, or where does the analogy break down?
I think it's for two reasons, right? And one reason is that you have to remember that natural evolution works, but is extraordinarily slow. The entire surface of the Earth is a massively parallel supercomputer that has been going on for 1 billion years, right? So maybe the algorithms that people have, if you give them 1 billion years in the supercomputer the size of the Earth, like in the Hitchhiker's Guide to the Galaxy, maybe that would work, but not very interesting for us right now, right? So you got to realize that, right? But the other, and in fact, there was a point, I remember going to these conferences where people lost faith in the evolutionary approach. And this was when there were these papers that came out saying, look, you're doing all this crossover, blah, 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 blah. I just do this brute force search and I get the same results in the same time. So people were just fooling themselves that evolution had done something, where they could just, they had small enough probes and enough computing power that, they came upon the right answer, right? Like, I can design a little radio just by randomly stringing, transistors and resistors together. And so like, hey, evolution did it. But apparently, the evolution was not really there, right? But there's another aspect to this, which I think is actually the most interesting one. And I can't prove it this is my guess, is that the problem, and again, it's the same problem actually with the connectionists and with a lot of other things, is that we don't understand well enough how evolution works. Natural evolution is actually far more sophisticated than this cartoon that we've implemented in computers, which is why it really pays for us to try to study better in collaboration with the biologists and have ideas going back and forth. So I like Stuart Russell. And again, if you talk to when I was writing the book and I told people, I ran it by a lot of people in different fields, like Jeff Hinton was one, to see what they thought. And one of the most common reactions were, oh, why do you even have the evolutionaries? Like this just died, right? So a lot of people wouldn't even have a chapter on that, which I think would be a huge mistake, right? But I think that there are a lot of if you look at natural evolution, it really does amazing things. And I suspect that the reason, this is actually more than a suspicion at this point, right? We know how evolution works far beyond Darwin at this point. And also far beyond, Watson and Crick. And there's a lot more, like gene regulation, for example. That whole thing, right? And epigenesis and whatnot. So I think I have I believe that very likely at some point the evolutionaries will have big contributions to make. So I'm glad that there's a number of people that haven't given up on it, even though almost everybody has. But it's because there's more to be discovered about how evolution learns. And by the way, there's more to be discovered for the purposes of AI and also for the purposes of understanding evolution, right? I actually think that if someone really had a supercomputer, right, that could, simulate evolution over 1 billion years with the model of evolution that we have today, it would fail. It wouldn't get there, right? There's some mechanisms that also evolve, but again, this is this interesting series of stages, right? Even within evolution, there are levels of how evolution works. And I think there's a lot of that we still don't understand, but we will at some point, and I think that will be beneficial both for biology and for AI.
So from an academic perspective, how do we know, whether or not a school of ideas is dead or simply dormant, right? I mean, we have limited resources in universities and in corporate labs, and we're in a what have you done lately kind of environment when it comes to funding and so forth. And so are efforts like yours helpful to kind of identify areas of potential insight? You need to, in order to do this, you need to know at least enough about that discipline. And in a world where everyone is highly specialized, you don't usually spend a lot of time learning about competing fields or adjacent fields or fields that seem inconsistent with your own. And if you do understand them, you typically are dismissive of them. So is your approach, which is kind of like a meta approach, one that is, unusual in the discipline? It seems like it would be pretty hard to, get a refereed journal article that is seen as advancing the field when it's really more of of this kind of, interdisciplinary. And I say interdisciplinary, meaning across different disciplines within the single discipline of computer science. How do you advance knowledge about the knowledge within your discipline?
Well, just to be clear, my approach is not at all unusual. There are a lot of people in the field trying to combine different things. So for example, right now, combining Mural and symbolic learning is a very hot thing in the field. There's thousands of papers about that coming out. So there's a lot of this happening. And there's been a lot of this happening, for decades, right? So there are like the individual schools, but there are also a lot of people trying to cross things, right? Where my book maybe goes a little bit further is in trying to unify all of them as opposed to just two at a time, right? You can do two, I basically run the gamut of combining any pair of these two in my career, but then you need to go and step for and say like, well, about 3 and 4, and what about all the 5, right? And then there's even this question, like maybe there's a 6th paradigm or 7th that we've been missing out, right? So just to be clear, there's a lot of people doing this, but you're also right, very right, that at any given time, and again, I think machine learning is not unusual at all in that respect. There is a dominant paradigm, and in some sense, it captures too much of the oxygen. It's not that there's something wrong with it. In fact, I was doing deep learning before it was hot, so I think deep learning is a great thing, right? But it has captured too much of the oxygen. Even some of the leaders in the field say that, right? Mm-hmm. But this is just natural human behavior, right? It's like a type of herding. And science, paradoxically, right? Finished science is what people see. And that seems very certain.
Well,
right?
Deep learning wouldn't have made the advancements that it made if you didn't have some stubborn person like Jeff Hinton just, persisting at doing something that really wasn't considered viable at the time, right?
No, that's my point. So, and in fact, Yoshua Bengio famously said, some journalist asked him, so, if you're a graduate student and you want to be the next Turing Award winner, Turing being, the Nobel Prize of Computer Science, what should you do? And Yoshua said, you should work on something other than deep learning, right? So there's a few good rules of thumb here, right? One is that tenure is good, right? There are a lot of zombie fields inside us, right? And you're like, why are those people still doing that, right? And most of them stay zombie. Mm-hmm. But one in some number, like deep learning, comes back, and that pays for all the rest. So I, as a researcher, have it as a rule of thumb that yes, I want to know what's happening in deep learning, but I'm also always looking to like, what are the things that are like very obscure? Because like I remember seeing a talk by Jeff Hinton in 2004, right? Back when like nobody cared about it. I was like, this stuff is really interesting. Like there's future. I mean, like I wasn't imagining just the scale of that future, but like, there's a bunch of other things like that now, right? And we'll see 10 years from now, maybe one of them will be the dominant paradigm. So I think there's like a natural centripetal force in research. We also need a centrifugal force. People need to, have this discipline of not just following the herd and looking for the next easy result. Unfortunately, of course, the incentives in this system, right, ironically promote short-term thinking, right? We know that the corporate world has to live in the short term, at least for the most part, but science is supposed to be where we worry about things 10 or 100 years out. But then what happens? It's like, I need to publish a paper to get, my degree and to get a job, a series of them. And the next deadline is, 3 months from now. What do I do in 3 months, right? And this, unfortunately, is very hard to combat and is very prejudicial, right? Because it leads to just, dwelling on the local optimum instead of jumping to the next better one.
Mm-hmm. Now, is there a guidebook to creating a unified theory? I mean, it would be nice if there was, in economics. I just had a podcast earlier where I was talking to someone who is a development economist, and I was saying, well, like, why isn't there just economics, right? Why is there development economics and labor economics and so forth? Is there a how-to manual? Can you learn from the construction of a unified theory in physics or biology? I think in the book you said that in order for us to have a unified theory of machine learning, you've got to have some unity in representation and evaluation and optimization. So is this sort of the playbook? You have to identify the key elements that have to be made consistent with one another before you can find the single theory?
Exactly. Right. And I mean, the details, of course, will be very different from what happened in biology or in physics, but the idea is the same. And again, you just nailed it. When you look at these algorithms at level, oh, this one is inspired by the brain and this one is evolution, they look completely different. But when you actually look at what the algorithms are doing, they're at some level, all of these machine learning algorithms are remarkably similar. They have a representation, they have an evaluation function, and they have an optimization procedure. And you can almost mix and match them any way that you want. And then these representations have very well-known relationships between them, in that one, suits the other, and so on and so forth. So a lot of these things we actually understand very well, right? And these algorithms have these theorems that say, if you give it enough data, this algorithm can learn anything. So we know that in the end, these algorithms, if you give them enough data, and if they are these powerful algorithms, as opposed to just linear regression, they will all converge to the same thing, right? So we actually have, in addition to the existence proofs, right? We actually have strong theoretical reasons for believing that this unification is possible.
And I think at the end of the book, you talk about what might be possible. And a lot of this, it's funny because it's 5 years old and the book, and yet at least I think, I read it in 16. A lot of these things are still, you could have written this today, and I think we would all still be saying, hey, these are some of the things that we would like to see, or that, we can envision seeing in the future. And you even walk through this little story where you have, Robbie the robot, and what would it mean to have, little Robbie the robot kind of do something similar to what humans are capable of doing. What will this open up? A lot of people talk about, AGI and at no point in the book do you use that term AGI. Is there some implicit AGI that would be enabled by this unified field theory?
Well, yes, absolutely. Right. I mean, AGI at this point is a loaded term that's associated with some ideas, but not others. But think of it in terms of human level intelligence, or intelligence beyond the human level, right? And even there, you have to be careful, because in some aspects, we're already way beyond human level intelligence, right? Doing addition and multiplication used to be considered something that required, intelligence and a certain educational level. And now it's like, what? But right. So, so human level intelligence itself is a very fuzzy concept. But if we do have the master algorithm, precisely what it enables is human level intelligence and beyond. And again, I do agree with this idea that we're not going to stop at human level intelligence. Once we figure that out, like the following day, we're already be beyond it, right? And that's when things really get interesting, right? And then interesting questions like, to what extent can we predict what that will look like versus we can? And, people like Ray Kurzweil was like, well, the singularity happens and we can't predict anything. Actually, we think that's far from the truth, because some things, will not change, right? The other aspect of this, which is actually very important, is that Well, why does my book not seem outdated at this point? Because, AI these days, every day in the news, there'll be some new AI development, but at the same time, at a deeper level, AI is an extremely slow moving field because AI is such a hard problem, right? The human brain is the most complex thing in the universe. AI is the hardest problem there is in the universe. And, we've made 50 years of progress. And now we made progress faster, partly because there's, 100 times or 1,000 times more people working. But we are still only, a fraction. It's like, we want to go to Alpha Centauri and, we've made it to Mars so far, which is something, but, that's whatever, 20 light minutes away as opposed to 4, right? So if you look at that deeper level, AI still has a long way to go. And a lot of the unanswered questions are still the same and they're still unanswered. Not because people are dumb, right? Like some of the smartest people in the world are AI researchers, because it's just so very hard. So, I would say even another 10 years from now, we'll have made a lot of progress, right? But a lot of, the questions about like, well, what can the robot do and how will he do that? They'll still be the same.
Now, one of the things that you talk about is this idea of automating the scientific process. Should our scientists be worried about their jobs, right? I mean, if we automate, it would enable incredible things if we could automate the scientific process. But does this mean that kind of the rest of the sciences will simply be subfields of computer science at some point?
Well, actually, on the contrary, right? The scientists that I've spoken to, they love the idea of automating science because their problem is that they don't have enough postdocs. Right? It's like, how would you like to, instead of having, 5 postdocs or, 50, if you're a big shot biologist, you had 50 million. And you didn't need to write all these NIH grants. They'd be like, oh my God, give me that now, right? So, and actually, there literally are machine learning systems these days that do the complete cycle of biology, including running the experiments with a robot arm in the lab. And they discover useful drugs and whatnot that way, right? Does this remove the need for the human biologist? Not really, because again, there's a lot of stuff that the human biologists know and can do that the computer can't. It just essentially gives that human biologist an army of millions of postdocs that never stop working. So what scientist wouldn't like that?
Mm-hmm. So it's been a couple of years since you wrote the book. Are you as optimistic, more optimistic, less optimistic? You mentioned computer science and machine learning moves slowly. Even though the rest of the world would probably not realize that. Are you more optimistic? Do you think that this is going to happen in your lifetime?
So there's different aspects of this. The speed of scientific progress, that has certainly picked up since it was already picking up, but that it's picked up since I wrote the book. But, science is not linear, right? Progress moves by sudden shifts and plateaus. So I'm pretty sure that at some point what we're doing now in one way or another will plateau, right? And a lot of good things will be there, just as there are now, right? That's where there would be another AI winter at this point. AI is an industrial reality. But how long it will take before we jump out of that plateau is very hard to predict, right? So will we get to human level AI in my lifetime? I really don't know. And I think nobody knows. If somebody says like, oh, we'll get to human level AI by 2047, they're, making stuff up, right? And deep down, right, it's like, Alan Kay said, right, the best way to predict the future is to invent it. How soon we get that really depends on us, our creativity and our ideas. So what I can do is try to, help speed up progress. In fact, as I say in the book, one of my aims was to get people who are not AI researchers to start thinking about AI because they might have the ideas that we, being stuck in our particular paradigms, are unable to have, right? So I think that there will be a lot of things like that. And, it's not so much that computer science moves slow. It's relative, right? If you get to Mars in an hour, you just move spectacularly fast, right? But in terms of getting to Alpha Centauri, that's still not that great, right? And compared to the speed of light, it is not that great at all, right? So what we can do is try to, speed the progress and avoid this trap of always falling into. We spend a lot of time in these local minima, right? Just refining things that, 10 years later is like, what was the point of all of that? So I think we can try to combat that. So this is one aspect. But unfortunately, these days, there are actually other aspects which are equally important. And something which I kind of like talked about in the book that this was going to happen, but it happened, to an even greater extent, is that, I mean, some of it was predictable. And again, is that like once any field goes from being some obscure thing that a few scientists are working on to something with real social impact, a whole different ballgame begins, right? Everybody's trying to get control of AI. No, actually not everybody. Some people and the other ones should be, but haven't woken up yet, right? And a lot of these people have very dystopian views of AI, and they want to limit AI in all sorts of ways that are well-intentioned. For example, access to data, and what you can do that is, I mean, let me give you one small example, GDPR, right? Europe's regulation on the use of data that everyone has to obey. It forbids using data for purposes that it wasn't originally gathered for. This is so harmful, right? Every interesting machine learning project I've seen was using data for a purpose it wasn't originally gathered for, right? X-rays, penicillin, lasers, blah, 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 blah. These are all things, data that was, right? Penicillin, like, he was trying to do something else, right? That went wrong, right? So, and unfortunately, the sum total of all these restrictions is to slow down the progress. Right? And then there's worries like, again, these are very old and not unique to AI, but like, oh, AI is good. We got to put brakes on AI because it's going to automation. It's going to kill jobs, right? It's going to cause a catastrophe. We're like, that's never what's happened in the past. You always get more jobs in the end than more lost, right? But here we are fighting that fight all over again, right? And then there's the people saying like, oh, Terminator, right? The machines are going to take over, right? Like, that's a joke, right? But again, the tendency of all these things is to put brakes on AI, right? In fact, what I believe, and I say that in the book, and it's been quoted a lot, right, is that the big danger from AI is not from machines that are too intelligent. It's from machines that are too stupid, right? The problem that we have in the world today is that there are real decisions, important decisions being made by computers that are not smart enough, right? That's what's dangerous. What is the big danger with, intelligent weapons? The big danger with intelligent weapons is not that they're going to get out of our control and decide, go down the street killing people like Elon Musk said. The real danger is that they're not intelligent enough and they kill innocents, just like humans do, by the way, right? So there's a lot of these perceived dangers of AI that are causing to people to push on the progress, but that frankly, I think, they're mistaken. This is not to say, very important note, that there are not things to worry about in AI. There are very much things to worry about, but unfortunately, these imaginary dangers are sucking up the oxygen and actually, subtracting attention from the things they really do need attention.
Well, natural intelligence has its problems too. So I think we've got to compare artificial to natural intelligence if we're going to make a choice. Pedro, thank you so much for joining me. I really appreciate it. It's always a treat. And I really enjoyed having an excuse to reread this book. It's still very fresh, and hope to see you in the Bay Area sometime soon.
This is Unsilo, brought to you by Alumni FM, connecting people through stories.